All right. So today we're going to cover an important theorem about planar graphs, the so-called Euler characteristic equation, which you may have seen already in a geometry or topology class. So Euler characteristic, oops, okay, I spelled that all wrong. Still not spelled right, but whatever. It's one of those mornings, you know. Anyway, so the Euler characteristic equation says the following. So let G be an n vertex, m edge. So our graph's got n vertices and m edges graph with a planar embedding. So just suppose G is drawn in the plane without crossing edges. Yeah, so maybe I should say that it's a planar graph, right? Only planar graphs have planar embeddings, okay? I will be emphasizing this, that when I talk about a planar graph, I'll emphasize, especially in this theorem, that we have a planar embedding. But usually if I tell you G is a planar graph, you can just imagine, oh, okay, it's drawn in the plane without crossings. We know that exists. Just assume that's how we're presenting it. But here I want to emphasize, and you'll see why we can get away with this, but now I want to emphasize that it has a planar embedding, and that's what we're discussing. So with a planar embedding with F faces, okay? So we've got a planar embedding and it has F faces, right? We discussed what a face is last time. It's a region that's bounded by a cycle, basically. Although not every cycle is a face necessarily. Maybe I'll give it, we'll draw a couple examples in a moment here. And I'll re-emphasize what a face is. But the faces are just the regions of the plane that the planar graph is broken into by repeated applications of the Jordan curve theorem. Okay, so if G is an n vertex graph, n vertex m edge f face planar embedding, basically, then these three numbers, n, m, and f, satisfy the following equality. If you take the number of vertices minus the number of edges, oops, and add to it the number of faces, then that quantity always equals 2, okay? Except I made one small mistake here. G needs to be connected as well. Does it need to be connected? Yeah. Connected. Right. It needs to be connected as well. If it's not connected, there's a like you can put a components parameter into this thing here and still get the equation to work. Maybe we could derive that later. It's not really hard, but usually when we talk about planar graphs, we just assume they're connected. In fact, virtually always when we talk about graphs, we just look at connected graphs anyway. All right, so it satisfies this equality here. Let's maybe test a few examples real quick here, and I can re-emphasize what a face is. Okay, so here's the first planar graph we've seen a number of times, the K4, and this has 1, 2, 3, 4 faces, right? The outer face, and in this example here, actually every cycle of this graph is a face, but that's not true in general here, okay? There's 4 vertices. What? Oh, yeah, okay. Can't do arithmetic. 6 edges, 4 faces, and this does sum up to 2. So this, I mean, it should and it does satisfy. Yeah. Let's look at the hypercube, or this is just the ordinary cube, if you like. The first one was the tetrahedron. And this is actually nice to think about for a second here. Just here's an example where you have cycles that aren't faces, right? If like you take this cycle here, right? That's not a face. Like that is a cycle in the graph, but it's not a face. It's 2 faces glued together there. Okay, so every face is a cycle, but not every cycle is a face. Something to keep in mind. Okay, and let's just check this one real quick here. There's 8 vertices here. How many edges? Actually, the graph I believe is 3 regular, so we should be able to get it there. I think it's 12, right? Every degree has 3 edges coming out. You can count it too. And then how many faces are there? 1, 2, 3, 4, 5, and then the outer face, 6 plus 6, and I believe that adds up to 2. 6 plus 6 is 12. 8's 2 more. So, okay, great. Both these seem to satisfy it. Obviously, that's not a proof, but that's the starting maybe 2 examples here. And it's of some note here. This is a tetrahedron and this is a cube. These are both Platonic solids actually drawn as planar graphs. And if you've seen the characteristic equation before, you probably saw it in reference to Platonic solids. The Platonic solids, so the icosahedron and the dodecahedron and the octahedron, all satisfy these things here. In a geometric sense, usually we talk about it originally, right? The vertices, those are still called vertices, right? Those are the corners of a polyhedron. The edges are just the boundaries between faces. The faces are clear what they are in polyhedra, right? We actually literally use these same terms. They just refer to geometric things. But it turns out those polyhedra are just planar graphs in disguise. And the way that works is, I mean, this isn't really important because we're not going to talk about them, but if you draw these on a sphere, you can project them down onto a plane in a way that doesn't have any crossing edges. So every polyhedron is actually a planar graph in disguise. But there are tons of planar graphs that have nothing to do with polyhedra, right? So this theorem on planar graphs is a lot more general. Although, you often see it proved in geometry or in topology as well. So it holds in multiple places, but we're going to do it for planar graphs. But along the way, it proves it for polyhedra, modulo that argument that the polyhedra are actually planar graphs. You have to convince yourself of that. Okay, so there's like 20 different proofs of this theorem. It's awesome. It's really cool. So today we're going to do 3 or 4 depending on time. So yeah, let's do proofs number 1 through 3. I'm not going to do these. I'm just going to tell you. You can prove this by doing induction on n or m or f. Any induction on any of those 3 parameters works. If we have time, maybe I'll do on edges at the very end or something like that. But induction on n, m, or f. Okay, any one of those works. The base cases of all of these do require a little bit of topology or a little bit of thought, but the inductive hypothesis, I mean, the inductive step's like super easy in all of them. You just remove an edge or you remove a vertex or you somehow try to figure out how to remove a face. It's basically equivalent to removing an edge. And the thing kind of falls out. Anyway, if we have time, I'll jump to do one, but they're the least interesting, least illustrative. I want to give the other ones that are a lot more fun. The textbooks probably have the inductive proofs, would be my guess. I don't remember off the top of my head. Okay, so proof number 4. This is a personal favorite of mine. This requires Ferry's theorem, the straight line embedding of the graph where we can draw it with straight lines. And it uses geometry, which is cool because usually the first thing you tell students, and maybe I didn't emphasize this, is that despite the graphs are drawn in the plane, there's no real geometry that we can use when we draw them in the plane because edges are not straight lines. Yes, in these examples they are, but before we have Ferry's theorem, we just say, hey, you can draw it. But if you don't have straight lines, like it's hard to talk about geometry because geometry is like, the study of angles. Like you don't have angles when you have curved lines. Like that doesn't make any sense. You need straight lines. Fortunately, Ferry's theorem says, hey, if you're planar, you can draw with straight lines. And then you can say, okay, pretend it's drawn with straight lines. Now we can compute angles and stuff like this. This is highly unusual, though. I think this is the only place in graph theory or in planar graphs where like the angle between edges happens, right? Because remember, the drawing of a graph is just a representation. Like you can move things around. There's no angle between edges. But if you do have a drawing, you can talk about the angles in that drawing. Okay, so let's illustrate. Okay, so consider. Okay, so okay, how does this work? We have a planar embedding already with f faces. Okay, yeah, so there's one fact we basically need that follows from the proof. We're going to use it here anyway, despite the fact that we're going to prove it. Notice one consequence of this theorem is that the number of faces is fixed in any embedding, right? Now, you can solve this equation for f, and like f has to be the same no matter what the planar embedding is. It's just 2 plus the number of edges minus n. That's the number of faces. So like it doesn't matter. No matter what embedding we have, there'll be a fixed number of faces. That follows from the theorem, so we shouldn't use that fact in the proof, but in proof 4 here, we're kind of going to use it, okay? Because like suppose our planar embedding is has straight lines, okay, via Ferry's theorem. Okay, so we can only really apply this if we can convince ourselves that if I give you a planar embedding and I transform it into a straight line embedding, that I don't mess with the number of faces, right? Like I'd need to be able to do that. Like maybe when I change via Fairy's theorem to a straight line embedding, I lose or gain faces or something like that. I mean, we don't because of this theorem, but a priori, we don't actually know that. So you're actually gonna have to take that as faith. That can be proved, but we're just gonna take that as a fact that our planar embedding has straight lines. We're just gonna assume that, okay? Okay, so now what I'm gonna do is like, here, let's draw like an example graph over here that we're gonna work with. I don't know. No. So there's a planar graph that's with a straight line embedding. And what we're gonna do is around each, we're gonna sum interior, yeah, okay, angles of each face of G, including interior, this part's a little weird, of outer face. Put this in parentheses. Okay, so each face is a cycle. Moreover, each face is a polygon, not a convex polygon, but possibly a concave polygon. But for each one of them, I'm going to sum up the angles. So like this triangle here, I'm going to add that angle plus that angle plus that angle. I'm going to add those up, okay? For this triangle here, add this plus this plus this. For this funny looking face here, I'm going to add up this plus this plus this plus this plus this big angle, but that's okay, right? For this one, I'm going to add up these angles and this one here. And then I do, the exterior face is also a polygon, but I don't want to sum the angles out here. I'm going to sum this angle here. Okay, so on some occasions, the same angle will get counted twice. And this angle and this angle. Does it make sense, right? My drawing is just a bunch of embedded polygons. I'm just going to add up the interior angles of each one of them and add it across all faces of my graph, okay? Now, anybody remember from, I don't even remember when I learned this, but the sum of the interior angles of a polygon has a formula. There is a formula for it. So recall. Look at that, Van remembers. Okay, sum of interior angles of a k-gon is k minus 2 times pi. That's the sum of the interior angles, or times 180, if you like, of a k-gon. Okay, so a triangle is just pi, that you probably remember, right? The sum of angles of a triangle is 180. Larger polygons, convex or otherwise, sum to this thing here, okay? So what does that mean? That means that when we compute this sum, what am I saying here? Yeah. What? Why is that? Yeah, okay, now observe that each edge of G contributes to two faces, right? If we have an edge, there's a face on either side of that edge, right? That's how planar graphs work, right? This edge has a face here and face here. This edge has a face here and face here. This edge has a face here and face here. I didn't add the angles here. Oh yeah, by the way, in this funny one, I missed an angle, right? This interior angle wasn't summed. And then I didn't actually draw the triangle here. And actually this angle as well I missed, right? There's an, even though it's like a straight line. Okay, so now I think actually every angle is marked in this example picture, right? Did I miss anything now? No, I don't think I did. Okay. So total sum is, okay, so let's think about this for a second. The sum of the interior angles of a k-gon is this quantity here. Now, when I looked at this k-gon, it was a 1, 2, 3, 4, 5, 6, 7 gon. This was a 3 gon. This was a 3 gon. This was a 3 gon. This was a 1, 2, 3, 4, 5, 6 gon. And the outside was 1, 2, 3, 4, 5, 6, 7 gon. So if I add up this value over all the k-gons, k is changing, right? Each face contributes a different k, depending on the size of that face, the number of edges on that face. So if I add up these for all the k-gons, Each edge appears twice. So the total number of k's across the whole thing is twice the number of edges of the graph, right? Like if I add up the length of all these k-gons for the whole graph, it's 2 times the number of edges. Does that make sense? That's a like nice little double count argument, but every edge appears twice. The total number of edges is two. So yeah, I mean, if like I could write the thing like this, like, I don't know, let's say k of f, this is over every face, k of f minus 2 pi, where k of f is the length of the cycle f, and I sum up over all cycles. This sum here, this k of f value here sums to the number of edges, okay? So that this total sum here is 2 times m minus 2 times f times pi. That's the value of this sum that I get when I take the whole thing. Why? The number of terms in this sum is f, right? Is that okay? I'm using two. Little f here represents both a specific face and the number of faces. So it's a bad abuse of notation, but I wasn't planning to write this equation here. Okay. Anyway, you don't actually need this thing here. You can conclude this guy here, right? If I sum this thing here over every face, the total at the very end will be 2 times the number of edges minus 2 times the number of faces, because this minus 2 here appears for every face, times pi, okay? But if you look at this picture that I've drawn here, at least most of the time, notice there's an alternate way to compute this sum. Like look around a typical internal vertex, right? Like look at this vertex here, or this vertex here, say. What is the like total angles around that? What have I computed along the way here? Of these all red arcs, there are 3 red arcs here corresponding to the 3 faces of that vertex. Adding up those 3 red arcs sums to 2 pi, right? Sums to 360 degrees. Same here, same here, same here. The exterior vertices, they're a little bit different, right? The exterior vertices seem to sum the interior twice, right? Red plus red plus red and blue. But that's not equal to the outside angle here. Like it kind of depends on the angle around this outside one. Okay, so it's not quite this, but this is what I want. So on the other hand, for each internal vertex, right? Internal vertex is just one that's not on the outer face. The sum adds all incident angles for a contribution of 2 pi, right? Just scroll up here again, right? If I'm looking at this same computation here, summed in a different way, like vertex by vertex by vertex, on an interior vertex, I get a contribution of 2 times pi, right? We observed that already. For an exterior vertex, I get something a little bit different. So for an external vertex, let's look at an illustration here to help us out. So say this is a vertex on the exterior. There could be multiple faces along the way here. And we sum up the internal angles for each of these. And later, we also sum up the internal angle for the fact that this is an outer face at the same time, right? Just look at the picture here. Like this example, right? The sum of the interior angles of the interior face and the interior angle of the outer face. Maybe this one's an even better example here. Red, red, red for the 3 faces here. And the 4th face, instead of adding up this outside angle, I add up this inside angle. Why did I do that? So that this count here actually works. If I don't do that count here, I get something weird here, okay? So let's actually draw that a little bit differently. So there would be a blue angle just going here, but let's redraw it in a different fashion. Let's draw it this way. Oh, let me draw this with dotted lines. So let's extend these 2 like this. And then the blue angle here across the whole thing here is just the same as this one here. Okay, maybe I should put it in blue to be consistent. Right, those are the same. I just drew the blue one up here to take it away from down here, okay? I extended these 2 guys here. So for an external angle, vertex x, say this is vertex x, the contribution is 2 times pi minus something, right? Minus something. because like these red ones plus this blue, the blue ones aren't going to eat up everything, right? There's this leftover excess here and here that isn't counted there. And that just depends on the angle at this point here, okay? So it's 2 times the sum of these interior angles, or in other words, it's 2 times pi 360 minus these 2 green regions here. These green regions have a special name though. If you have a polygon, I'm going to keep it convex, just it's easier to draw. And I extend them like this and compute these angles. There's a special name to these angles in a polygon. Anyone remember their geometry? These are called the exterior angles of the polygon. It's not the full region around here. It's these extended pieces here. These are called exterior angles, right? These are ext angles of polygon. Anyone remember the formula angle thingies? Yes, thanks, man. Anyone remember this? This may sound familiar. The sum of exterior angles of a polygon. Anybody remember the formula for that? So let me write this first. I don't know what they are. I'm going to write alpha of x. Oops. I'm going to write 2 times alpha of x. This is the alpha of x's exterior angle at x. Okay. So that's this thing here is like, this is alpha of x. This green strip here is alpha of x. That has a special term. If you take a polygon, okay, I think I'm back. All right. So I was saying, if you take a polygon and compute these external angles and add them up, you always get 2 pi. It doesn't matter what your polygon is. It's fixed 2 pi. And it kind of makes sense, like if you remember your geometry, but if you have a triangle, your exterior angles are big, but there's only 3 of them. If you have like a, crazy huge, almost circle gone, then you have lots of them, but each of them are like small. Like the angles here are I froze again. Oh, not 180, sorry. They're really small here. They're like approaching, exterior angles are approaching 0, okay? Always adds up to 360. I'm not going to prove that. That's from geometry, okay? But at any fixed point here, I don't know the size of that exterior angle. It could be big, could be small. Depends on the angle, right? I don't have a regular cake on here. Okay, but sum of exterior angles is 2 times pi. So now let's recompute. Let's go back up here. Let's recompute the sum of all these angles, vertex by vertex. So at each internal vertex, I get a sum of 2 pi. I get a sum of 2 pi at each internal, 2 pi plus 2 pi. At an external vertex, I don't get 2 pi. I get 2 pi minus 2 times that external angle, right? Because this should be in green. Right, I miss this much and I miss this much. So those angles are the same as each other, so I miss 2 times the exterior angles. So in total, I get 2 pi contribution for every vertex. I froze again. All right, I'm going to close some tabs. That seemed to work when we had this problem last time. Okay, let's see. Hopefully we don't pause again. Yeah, so if I sum all angles around vertices, I get 2 pi for each internal angle. For each external vertex, I get 2 pi minus 2 times the corresponding exterior angles here. But in total, those exterior angles add up to 4 times pi, right? 2 times pi times 2. So summing angles at vertices gives a total of, why didn't I write that down? Yeah, it should be 2 times pi times the number of vertices. So each vertex contributes 2 pi, except for the external that come up a little bit short, but the total amount they come up short by is 4 times pi across all the external vertices. It doesn't matter how many external vertices there are. At the end of the day, they'll contribute the sum of the exterior angles twice, which is 4 times pi. So the sum of the angles by vertex is this, And the sum of the vertex, the sum of the angles by edge is this, 2m minus 2f times pi, 2m minus 2f times pi. And now we're done here. Divide both sides by 2 pi, and we get our equation. This becomes 2. These cancel. You have n minus m plus f equals this 2 is left over. And that's the end of the proof. Okay, so we used a bunch of geometry. The 2 pi's that were around the whole time just vanished. They canceled out, and we got the equation here. Okay, this proof is the one you would want to use in geometry for proving polyhedra. You could actually use this proof just fine here. This barely relied on graph theory. Basically didn't, well, it did rely on a little bit of graph theory, but mostly it relied on straight line embedding. Okay, all right, good. So that's proof number 1. This is one of my favorites. It's kind of neat, especially when in most classes I don't teach Fairy's theorem, and so you spend all this time talking about embeddings, and then you like say, oh, hey, if you have a straight line embedding, which you'll have to trust me you have, then you can prove this. Okay. All right, so let me give another proof. This is number 5, I guess. And this is what's called a discharging method. This is a powerful method in planar graphs. It's not something we're going to talk about in this class beyond this example, but this is like an awesome mechanical sort of proof here. Okay, so let's say we got our planar embedding, and I want the planar embedding to satisfy a certain property. Graphs embedded in the plane, I don't want in my drawing any 2 vertices to fall on a vertical line. Okay, so think about vertical lines in the plane. I want my drawing to avoid 2 vertices being directly above each other in the drawing. Okay, so so arrange the planar embedding of G such that no 2 vertices fall on a vertical line. Let me just emphasize, right? We're in R2. We're in the plane. So I'm talking about the line isn't an edge. I'm just saying there's no vertical line in the plane that hits 2 of my vertices. Okay. So first of all, I have to justify this statement here. This is a little thought experiment. Say you give me a planar embedding, right? So say like you gave me the K4 and it's drawn like this. Like this is bad, right? Like this is drawn in such a way that this vertex is directly above this vertex. I don't want that. But maybe my planar embedding has that. Maybe it has it in multiple places. What's an easy operation I can do to this drawing to avoid that and not change the number of faces or really alter the graph in any way? What could I get away with? Anybody see a trick? There's a couple ways of doing it. One way, and usually the easiest, is just if you have 2 vertices that are on a vertical line, just slide them both by some epsilon amount, right? And you can make epsilon as small as you want so it has no local effect. But you might have to do that for multiple vertices simultaneously. And so you want to make sure that shifting this one over doesn't make it fall on a vertical one here. And so like you can prove that it's fine, like if you do multiple shifts such that you start with epsilon, then shift by epsilon squared, epsilon cubed, or whatever, something like that, you'll be fine. But there's actually an easier way. If you just take the entire picture and rotate it slightly, then any vertical things will be avoided by the appropriate rotation. Just rotate by a very small amount and they'll all be deleted simultaneously. So we can get this via rotation. Okay, that also requires a little bit of thought, but by an appropriate small epsilon rotation, nothing will be lined up after that rotation. Okay, anyway, I don't think it's hard to believe that you can draw it by and avoid vertical lines. So just emphasize how we can actually get that. Okay, and actually, even if you still have it, this proof works with one little caveat. It's just much cleaner if you don't have that. Okay, so now what we're going to do is to each element of this graph, so each vertex, each face, and each edge, we're going to assign like an electrical charge, like a plus charge or a minus charge. Okay, these are just labels, -1s and +1s, but it's better visualized as electrical charge. Okay, so assign charge plus. So there's only 2 types of charges, and I'm not defining a charge. It's a label plus to each vertex. Maybe let's draw an example to do this with as well. Okay, these shouldn't be on a vertical line. That's like the one rule I have to obey. I don't know. I want this one to be Kind of interesting. Okay, so assign a plus to each vertex. So plus, 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 fine. Assign charge plus to each vertex, a minus to each edge. So you have a minus sign, and I like to think of this sign as being in the middle of the edge. Okay, so you have a minus on each edge. And a plus to each face. So on the inside of each face, I draw a plus. And then there's also a plus, like the exterior face is also a face, so there's like this extra plus kind of floating out here. Okay, so just assign pluses and minuses to all these elements here. And what I'm going to show is that these pluses and minuses, if I cancel a plus with a minus, everything here cancels except for two pluses. And that actually will prove my theorem, right? Because I have n pluses, m minuses, and f more pluses. If I add these three quantities, minus m plus f, that's the total number of charges there. If the charges cancel and I'm left with 2, then these three numbers sum appropriately to 2. Okay, so we show that charges, so all charges, let's just say charges cancel and leave 2 pluses, which implies that n minus m plus f equals 2, which gives our theorem there. Okay, and I'll even tell you in advance, this plus here and this plus here on the leftmost vertex, those are going to be the 2 pluses that don't cancel. All the other vertices, all the other pluses and minuses are going to cancel out with each other by a cool observation here. Okay, so what I'm going to do here to argue this is I'm going to take the charges and I'm going to physically like move them. Okay, and when a minus hits a plus, they like cancel each other. When 2 minuses hit each other, I have 2 minuses, right? Minuses and pluses cancel out. Okay, you can I don't know, you think of these as like electrons and anti-electrons or something like that. You'll be left with 2. Okay, anti-electrons are positive, electrons are negative. I don't know what I mean. Well, maybe, yeah, anyway. Okay, okay, so examine any vertex but the leftmost. Okay, so this is where my avoiding vertical lines came in play. I actually should have emphasized that. If I have no vertical lines, then I can arrange my vertices in order from left to right. Right? There's a defined order in terms of their x-coordinate from left to right. That's the only reason I didn't want 2 vertically. So there truly is a leftmost and a rightmost and a 10th leftmost or whatever vertex, right? They're ordered left to right. Okay, so examine any vertex but the leftmost. And what I'm going to do when I'm looking at that vertex is move the minus charge on, okay. Actually, let's see here. Do I know? You know what? I don't even need to examine. I don't even need that actually. I'm gonna examine the vertices after. Yeah, I'm gonna explain the procedure and then we'll examine the vertices after, I guess. I don't know why I even said that. Okay, so move the negative charge on edge to the rightmost right vertex. Okay, so each edge is between 2 vertices, and there's literally a left vertex and a right vertex, right? That now makes sense because of the arrangement there. So all these negative charges, I'm just going to slide towards the vertex to the right. Okay, this one goes up to here, this one goes over here, and so on. I'm not going to draw them all. Okay, they slide to the vertex to the right. The same thing's going to happen for the face. Move plus charge on, a face to rightmost vertex on that face. Right, so you got a face, and there's a well-defined rightmost vertex of the face. Again, because of the ordering, it's this one in this picture here. Draw it to the rightmost. Okay, so that's the procedure. So I'm just taking all these pluses and minuses and shifting them to the right here. The outer face, so yeah, on inner face. Okay, the outer face I don't do anything with. and I don't shift vertex vertices. They just stay where they are. Okay. Actually, there's a way to do that too, but we don't need to do it. Now I'm going to examine a vertex that's not the leftmost. Okay. Why don't we examine the leftmost? Well, look at the leftmost, nothing happens. It has its plus and nothing gets shifted into it because the leftmost is not the right side of any edge or of any face. Obviously, it's the leftmost vertex. But in any other vertex, let's actually look at one for a second here. This is maybe the most interesting one here. Take this plus here and see what happens. This got a minus here, and then a plus from this face, and then a minus on this edge, and then a plus on this face, and then a minus on this edge here. Okay, so it got minus, plus, minus, plus, minus. And I mean, this plus here doesn't go to, it might in principle go to this vertex here. And in fact, maybe we can allow it to at the end. But the rightmost vertex of the outer face is the rightmost face of the picture. Okay, this vertex here, say, gets, what does it get? It doesn't get the plus from the outer face. So it starts off by getting this minus edge here, that slides into there. Then it gets the plus on this face here. Then it gets the minus on this edge here. And then it stops, right? Because the next face is that thing there. And there's like an edge there, but that edge doesn't go to that vertex. It goes to the right. So it just looks at all the things to the left of it and shifts in there, okay? So examine a vertex but the leftmost. So say something like this. And what does it get? It has edges that contributed minuses to it. These edges over here don't have anything to do with it, right? They're to the right. So the edges to the left, whoops, send negatives to it. But between each of these edges, there's a face for which that vertex is necessarily the rightmost as well. So plus, 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 and then no man's land here and here, right? Nothing happens for this. And there was a plus here. But notice what goes into that vertex. So vertex X, not the leftmost, it gets an alternating sequence of minuses and pluses ending with a minus and starting, ending, and so, pluses and minuses, and start with a minus. Okay, it gets an edge. Eventually that edge reaches a face that doesn't contribute there, right? And so the total charge at X after doing this procedure is what? It absorbs one more minus than plus, right? Because it starts with a minus and ends with a minus. Like you can see this cancels with this, 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 and I have an extra minus left at the over end, which cancels with the plus that was already there, okay? So the total charge on a vertex after I do the shifting is 0, okay? Except for 2 instances. Let's go back up to the original picture and see what happens. 2 instances. This plus did not get moved. It's still there at the end. And this plus actually does get shifted to this vertex if we want to define it that way. But the same thing happens for this guy. Otherwise, it's minus, plus, wait, where are we? This is, minus, plus, minus, and then an extra plus that the other ones didn't get, right? The other ones didn't end with a face, they ended with a vertex. But the rightmost ended with a plus. And so everything cancels on this one except for this extra plus here. And so I'm left with this plus and this plus at the end. So I get 0. I mean, I get 2, which is what I wanted, okay? Yeah, so maybe even, so not leftmost, not rightmost, say. Okay, and left and right vertex each have plus charge left, or remaining, let's say. So total charge is plus 2. And that's the end of the proof, right? Because now we know the vertex charges are n, the edge charges are negative m, and the face charges are f. And so when we cancel those things out, we're left with 2. So n minus f, m plus f equals 2. That's the method of discharging, right? Descriptive term. We put charges on the vertices and play with them. If you don't like charges, you can just do pluses and minuses and sum the things and so on. But I think the charges are really a nice way of thinking about this. Okay, so that's a great proof as well. Now let's do one final one that's a real treat, because this is a new proof. This was discovered by like an undergraduate in Texas, like I don't know, 5-10 years ago, and it relates two things that have similar names but have nothing till now to do with each other. So this is the Euler characteristic function. We also know about Euler tours, right? Both by Euler. They don't really have anything to do with each other. One's about the faces of a planar graph. The other's about can you walk around the edges of an Eulerian graph, right? A graph with all degrees even. It turns out they are related to each other somehow, even though like Euler was not aware of this connection, presumably. Okay. So first of all, a planar graph doesn't necessarily have an Euler tour, right? A planar graph might not have all degrees of even. Like it's not clear. So somehow we have a planar graph. We're going to want to make it have an Euler tour, and then somehow have that Euler tour tell us about the faces. Okay. So first, let's think about this. So in an Euler tour, forget about planar graphs for a moment. I'm just going to make an observation about an Euler tour. Let R count the number of returns to vertices. So what do I mean by that? I don't have a ton of time here, but say my picture is something like this. Then the number of returns is the number of times I visit vertices for a time past the first time, okay? So say I started this vertex, go here, go here, go here, go here. I'm now returning to this vertex, so R increments by 1. And then I go here. That's not a, that's also a return, actually, I think. I think that's a return. We'll see in a moment. Does that make sense as a return? I guess, yeah, I think it counts as a return. So this R equals 1, and then R equals 2 here across all. Maybe a better example would have been like, do another thing here. And this would add my R up again when I came around here. Hit it once, come around, hit it twice. Okay, does that make sense? So just have this counter that like each time I visit a vertex for the first time, R does not go up. But if I re-enter a vertex, R definitely goes up. Okay. So I mean, you can predict what R is going to be. It has to do something with degrees because this degree is 2, R will be 0. R will only get a contribution of 0. But if it's 4, then I have to return. If it's 6, I'm going to return twice. If it's 18, I'm going to return 7 times or whatever it is, right? So like we can predict how many returns there'll be, and R is the number of returns over the entire tour, including. I think we include this last thing at the end here. We'll see in the proof whether we want that to count or not. Okay, after the first visit, yeah. Okay, so an Euler tour makes the number of edges of G steps. Right, each edge is a step of the Euler tour. So total number of vertex visits, not returns, but total number of visits is the number of edges of G plus 1. Right, you started a vertex, and how many steps does an Euler tour take? 1 for every edge. That's what an Euler tour is, and it returns to where you started. And so how many visits are there? Well, here's visit 1. We started somewhere. Then I traveled along an edge, made another visit, another visit, another visit, another visit, another visit, and so on. Does that make sense? It's just the number of steps plus 1 is how many visits I make. But there's a close relation between the number of visits and the number of returns because there's only so many vertices. Okay, so the number of total returns is the total number of visits that I make. That's how many visits I make, minus the number of vertices, right? The first visit to each vertex doesn't count as a return, right? But every visit to a vertex after that first does count as a return. So if I take this many steps and this many of them are not returns, all the remaining steps result in returns. Does that make sense? So this is R, and actually this clarifies, yes, that this here counts as a return. When I get to the end, that also counts as a return, okay? So that's what R equals. Now, make the following observation. If G is planar, so say our graph is planar and we do this Euler tour on the graph, and it has an Euler tour, then, so say it's planar with capital F faces, then the number of faces is equal to the number of returns plus 1. Let me justify this, okay? As each time an Euler tour revisits, returns to a vertex, it closes off a face. Let me illustrate this by a picture. You can think about this a little bit. So say my Euler tour is walking around, and then it reaches a vertex for the first time, and then it continues. And then eventually it returns to this vertex, suppose. How does it do that? It has to travel as follows. And maybe it closes off other faces in the meantime, but eventually it returns here, and like maybe there are other edges along here. But the point is it goes here, travels along, and comes back. And now this face has been enclosed. And it may walk out again and then come back again, closes off another face. Okay? It's hard to see individually. You have to think of it kind of globally. Each return closes off a face. Okay? Plus one, the outer face. Right? Outer face is not closed up by this procedure. That's left over at the end. Okay? So number of faces is somehow related to the number of returns here. Okay, so we have two formulas for R, and notice that they relate the number of edges, the number of vertices, and the number of faces in some fashion, but we can't use this theorem directly because this only works if our planar graph has an Euler tour. What if I give you a planar graph that doesn't have an Euler tour? Then I can't talk about returns, so I can't use this, okay? So now let's suppose, keep this in mind. So suppose G is a planar embedding of a planar graph, okay? What's an easy trick to transform a graph into a graph with an Euler tour? We have an Euler tour if all degrees are even. What's a hack to transform a graph into a graph with an Euler tour?
You just go in and add edges until everything is even.
Yes, exactly. In fact, let's even do it in the following way, even simpler. Just duplicate every edge, right? If we duplicate every edge, then every degree becomes double what it was, so it becomes even. Like some were already even, but whatever. I mean, this like easily does it. Okay, duplicate each edge. Okay, now we have to think about what this has to do, what's going on in planar situation here. When I duplicate an edge in a planar graph, I had an edge here, and now I duplicate it like that. Is it going to be planar still? Again, use a little topology. Just draw the duplicated edge super duper close to this one so that it doesn't affect it. There's no crossings. So like even if edges come up like super close to this guy here, just make sure you don't interfere with this thing. Make it so tiny that it doesn't interfere. So we're using a little topology, whatever. You just make it tiny. And then this creates a new face, right? This is like a tiny face. So duplicate each edge, thus creating new thin faces. Okay. Now Fairy's theorem doesn't apply anymore here. We talked about this last time actually. Like when we have multi-edges, like now I can't draw with straight lines anymore because like obviously one of these two has to be curved. But we're not going to use Fairy's theorem, so it doesn't matter. Fairy's theorem only technically holds for simple planar graphs. Okay. But so let G prime be resulting still planar graph. Okay, so the graph's still planar, as we argued here. Duplicating these edges just creates really thin faces, doesn't introduce crossings if we're careful how we do it. Okay, now let's make some observations about G prime. How many vertices are in G prime? That didn't change, right? The number of vertices in G prime is equal to the number of vertices in G. We didn't duplicate vertices. What about the number of edges in G prime? Well, that's easy. That's 2 times the number of edges in G. We literally duplicated every edge. And now the interesting one, I'm going to call this f of G prime. That's the number of faces of G prime. Right, so number faces. How many faces do we have in G prime? This is the one interesting part. We have all the original faces, right? Those weren't changed. Those still are around. But how many new faces did we get? We got 1 new face for each of the duplications. So 1 new thin face for each edge. So the number of edges of G. So this is new. I mean, these two are this is the same. This is duplicated. This is altered in a slightly different way. Okay, but now G prime has an Euler tour because all degrees are even. Right? We intentionally did it there. So now we can use our rule here R equals these two things here. Now these quantities are for G prime, so let's write them out here. Okay, so R is equal to number of edges plus 1 minus number of vertices. So R equals, what did I say, number of vertices? Shoot, no, number of edges, which is 2 times the original, right? 2 times the original number of edges, minus the number of vertices, which didn't change. Oh, well, there's a plus 1 here first. Plus 1 minus the number of vertices of G. That's one thing for R. The other thing for R is R plus 1 equals the number of faces in the new graph. The number of faces in the new graph is this quantity here, the original number of faces plus, the number of edges of the original graph. And now if you take these two equations and solve and substitute, notice what you get here. Let me put a minus 1 here and erase this here. And then just put the two equal to each other. I get this equals this, right? One of the E of G's cancels with one of the E of G's here. I have, what's going on? Yeah, a minus 1 on one side and a plus 1 on the other side. If you just simplify things, maybe I won't do the arithmetic because we're out of time here. We're left with which is n minus m plus f equals 2. End of the theorem there, okay? So the strategy is these returns to get two formulas that work for Eulerian graphs, Eulerian planar graphs. If I give you a graph, it's not necessarily Eulerian, but I can make it Eulerian easily, and I can not make it Eulerian easily, I can predict what's going on, right? I make that new graph and I can predict the number of faces, number of vertices, number of edges. If I couldn't predict that, then I wouldn't be able to solve this because I'd be like, well, I don't know how many faces are in the new thing. How do I solve? But here, there was this easy relationship between them. You plug them in and you get exactly what we wanted, okay? So like this is I think this is great too, because again, you hear Euler characteristic, Eulerian tours. Yeah, they're by the same person. It doesn't necessarily mean they're related, but actually they're related. And you know, Euler proved this stuff like 400 years ago, and like 5 years ago, someone figured this proof out. Like I think that's a cool lesson too. There are beautiful, simple proofs still out there to be found of classic theorems. Okay.